Everyone, welcome to Building Distributed Message Log from scratch. My name is Tyler. I am a managing partner at Real Kinetic, which is a consulting group that helps companies build cloud software, but I have a particular interest in distributed systems, messaging systems, really just infrastructure in general. And I am a former core contributor to the NATS project, which is an open source messaging system. I'll talk a little bit more about that in just a minute. And I have a blog, bravenewgeek.com, where I write about a lot of this kind of stuff. So if you're interested in distributed systems or messaging infrastructure, you can go and check that out. So as I mentioned, I used to be a core committer on the NATS project. NATS is an open source, high performance messaging system written in Go. It was originally written as part of Cloud Foundry. And there's kind of two main projects within the NATS umbrella. There's the core NATS server, which is a high performance, lightweight pub sub system. And then there's NATS streaming, which is a streaming data layer on top of NATS. So I worked on both of those. I'll be talking a bit about NATS streaming in this session. And what we're talking about today is this idea of the log. We'll talk about what that is as an abstraction, why it's useful, but we'll spend most of our time talking about the implementation details. So the storage mechanics, data replication, scaling message delivery, and then we'll wrap up with some trade-offs and some lessons learned, things in particular that I learned while working on NATS streaming. So what is the log? When you hear that, you probably think of application logging or system logging, and really those are just applications of this broader idea, which is a totally ordered append-only data structure. So application logging is an example of that, where we're appending new log messages to the end of a file, for example. And so we have this ordering of events. We have a notion of events that are older, events that are newer, and fundamentally that's all the log is. And so it's really not a new idea by any means. The log records what happened and when. And so when we take that idea and abstract that, we end up with this really useful primitive. And in particular, when we use this as this central piece in our data infrastructure, we can write all of our data, all of our events in our different systems to this log, and then read those back from various services or caches, databases, indexes, and so forth. That becomes really powerful. And there's a really good blog post by Jay Kreps, one of the creators of Kafka, that really goes into depth on this topic, much more than I can in my 30-second synopsis. And so if this still doesn't really click for you, definitely go and read that. And it does a much better job of talking about that idea. And so there's a number of implementations of this out there, Kafka being probably the most popular, probably the first implementation of this as kind of a messaging type solution. Kinesis, which is Amazon's take on that. NATS streaming, as I mentioned, which is that layer on top of the NATS server. Pulsar is another one. And in this talk, I'll be focusing on Kafka and NATS streaming as case studies of sorts. We'll look at how those work, various implementation details of those. And in my opinion, there's really three important goals with this kind of system: performance, high availability, and scalability. And without all three of these, the value of this becomes a lot more questionable. And so we use these to help guide our decision making and guide our discussion as we talk about this. And really the purpose of this talk is sort of threefold. It's to learn a little bit about the internals of a log abstraction, how it can achieve those three goals that I just talked about, and also to learn some applied distributed systems theory. So there's a lot of research and a lot of theory in this space, and it can be kind of intimidating to approach that. So we want to take some of that, pull that into practice, and actually apply that to a real system. And you'll probably never have to build something like this yourself, nor should you want to. It's better just to take something off the shelf. But it helps to know how it works. And also, a lot of the things that we're going to look at, the techniques, apply to other problems you might come across. And so it's kind of that pattern matching on different problems and the solutions for those problems. And if nothing else, it's at least interesting, I think. So with that being said, let's dive in to the implementation. And I want to start by looking at the storage mechanics, how we actually store data. But before we do that, I want to lay out some first principles that will help guide our discussion. So the log is this ordered, immutable sequence of messages. We talked about that. And we don't necessarily care about the contents of these messages. We can just treat them as opaque blobs of data. But the messages are atomic, so they can't be broken up. So we have this sequence of these atomic messages. And the log has a notion of message retention. And this really is just a way to prevent our log from growing unbounded. So that could be based on the number of messages, time, bytes, etc. So I might say any messages older than 24 hours are just truncated from the log. The log can be played back from any arbitrary position, so I might read it back from the beginning, the end, or anywhere in between. The log can be stored on disk, so it's durable. And sequential disk access is fast. And I have an asterisk next to this to qualify that statement a little bit, which I'll do on the next slide. And lastly, the operating system page cache means that sequential access often avoids going to disk altogether. So as I said, sequential access is fast. You hear disk I/O and you kind of have this immediate reaction that, oh, that's really slow. But there's a little bit more nuance to that. And so this is taken from an ACMQ article, which at this point is actually kind of out of date, but it shows some of these things in relation to each other. And the second item is sequential disk. So there's a number of different access patterns, random, sequential, disk, solid state, RAM. And sequential disk is 53 million values a second. And you compare that to random disk, which is 316 values a second. Not surprisingly, it's orders of magnitude slower. But then also you compare it to sequential solid state, and disk is actually quite a bit faster. And so it turns out computers are pretty good at reading things sequentially, even from disk. And similarly, the page cache means that the operating system is going to take all of the unused RAM and basically use that to store pages of data. And so this is taken from a benchmark I ran with Kafka, where I just published a bunch of data to Kafka, read it all back, and then I ran IOStat, and you can see that blocks read and blocks written are both 0. And this is publishing, I think 1 million messages and then reading that back, and there's no disk activity. So the operating system is handling that behind the scenes. Okay, so we can start to think about how we actually lay this data out on disk. And we know that our log is this sequence of these messages, and these messages have a position, which is like a logical timestamp. And we can just store these messages in a file and just append new messages to the end of this file. And that works reasonably well. It takes advantage of that sequential scanning. But the problem is this file is going to get bigger and bigger over time. And so, doing lookup operations, aging out data, those operations are going to become more expensive the bigger this log gets. And so what we do, and this is what both Kafka and NAT Streaming do, is take this file and basically break it up into multiple chunks or segments. And so we end up with segments that store a subset of the log. In this case, we have just 2 segments. And then we have an active segment that we're appending new messages to. As that fills up, we create a new segment that becomes the active segment. And these segments have a base offset, which is the lowest offset stored in the segment. So we have segment 0 in this case, and segment 3. So segment 0 is storing messages 0, 1, and 2, and segment 3 is storing messages 3, 4, and 5. Okay, so we have a way of storing the data, laying it out, but we still need to be able to do lookups on that and also age data out based on those truncation policies. And so what we also do is, alongside these segment files, we store indexes. And these indexes just store pointers back into the log file, essentially. And so we have an index for segment 0 and an index for segment 3. And then within these indexes, we're storing pointers back into the log relative to the base offset. And what I mean by that is, for example, in segment 3, 0 relative to 3 is 3, 1 relative to 3 is 4, and 2 relative to 3 is 5. And by doing that, we can store those pointers just using an int32 as opposed to an int64. So we save space by doing that. Okay, so that's how we can store data. We can do lookups efficiently. We can do a binary search to find the segment that a message is in, do a search to find the pointer that points back into the log. From that, we can read sequentially. But I think it's also worth talking a little bit about how we actually read data back. And typically what that looks like is something like this, where I want to read from the log at a position, and so I'm going to issue a read system call. And what that looks like is, if that data is not in the page cache, the kernel is going to copy it from disk into the page cache. Then it's going to copy it from the page cache into my application in user space, and then I need to send that data out. And so I do a send, copies it from the application back into kernel space, into the socket buffer, and then finally it copies it out to the network interface card. So this is pretty inefficient. And what we can do to optimize that is do a zero copy read using send file, the system call. And the way that works is we basically avoid going into user space at all. And so send file will just copy the data directly from the page cache out to the network interface card. And we avoid going into user space. The caveat with this, however, is our data as it's laid out on disk has to be in protocol format. Right? It has to be in the wire format that we're actually sending out over the network. And so if we have to do any manipulation of that data in the application, then we're back here where we have to copy it into user space and then send it back out, which copies it back out into kernel space. And there's a number of other important optimizations. Batching and compression are two of the important ones, but for the sake of time, we won't get into those. Okay, I want to talk about data replication. So we have our log. We have a way of storing our data for that log. What happens when the host that data is stored on goes down? Then our log is unavailable. And so how do we achieve high availability and fault tolerance with this? And when we take that question and unpack it a little bit, we get a series of questions. And really what we're talking about with this is, how do we ensure the continuity of reads and writes with this system? And hopefully the answer is obvious, since I kind of hinted at it, which is we replicate. And so we get rid of this single point of failure by having multiple copies of our log. So if one copy goes down, I can fail over to a backup. And that, of course, brings us to the question of, how do we replicate the data? And generally speaking, there's kind of these two broad categories of ways we can replicate. With your gossip or multicast type protocols, that includes things like epidemic broadcast trees, bimodal multicast, and also like membership protocols. And then you have consensus protocols, things like two-phase commit, Paxos, Raft, and so forth. So there's a lot of different ways we can go with this as far as replicating. But one thing we have to keep in mind is, one of the important properties of this system is we have this consistent or the strong ordering of messages in our log. And so if I have multiple copies of that, and I go to read from one copy and I get one order, and then I read from a different copy and I get a different order, It's going to cause problems. And what that means is we need consistency with our data replication. Not just consistency of the orders, but also consistency of the message contents themselves. The contents should be the same regardless of which replica I read from. And so that more or less kind of rules out the gossip type protocols. Those tend to be stochastic or probabilistic in nature. They might be okay if we can get away with like eventual consistency. But for this system, we're really interested in strong consistency. And so what that leaves us with are these consensus type protocols. And it's worth pointing out that the way these protocols tend to work is we somehow select a leader. That leader is responsible for sequencing the operations in our cluster and then replicating those to the rest of the cluster. So I want to look at how replication works in a couple systems. First, looking at Kafka, and then we'll look at NAT streaming, how it works there, and kind of contrast the two because there's some similarities but also some key differences. So in Kafka, we select a leader. We won't specify how we do that, but somehow we elect a leader. And then we maintain this in-sync replica set, or the ISR. So this is the set of all of the brokers in the cluster that are currently up to date with the leader. So by definition, that's going to be all of the replicas at the very beginning. And all of the writes are going to go to the leader, and the leader is going to write those messages to a write-ahead log. So it's writing these to its own log, and it's committing these messages to its log once it knows all of the replicas in the cluster have also written those messages. And so the replicas are kind of these special consumers of the leader's log. They're just sitting there reading the leader's log, writing those messages to their own logs, and then the leader is committing those messages to its log once it knows that they're fully replicated. And the leader maintains a high watermark, which is the latest committed message in its log. And that high watermark gets piggybacked on the responses back to the replicas. So as the replicas are fetching messages from the leader, they're getting those messages, and then they're also getting that high watermark, and that's what tells them when they need to commit to their own log. And that also gets periodically checkpointed to disk for recovery purposes. So if a replica crashes, they come back up, they can get that high watermark that tells them where they're at in their log, and everything after that gets truncated because it's not committed. So this is what that looks like. We have our leader, all of the writes flow through the leader. The leader is writing those messages to its write-ahead log. These dotted lines, these are uncommitted messages. And so the high watermark is that point, the highest point that is committed in the log. And then the followers are just consuming the leader's log, basically, writing those messages to their own logs, tracking that high watermark, and that tells them where to commit in their own logs. And so there's a number of ways this can go wrong. I want to walk through a couple of the more important failure modes, the first being the leader failing. So Kafka uses Zookeeper for a couple reasons. One is as a failure detector. So when a node or when a broker fails, Zookeeper will be alerted of that. And the second reason is it uses Zookeeper to do the leader election. So when that broker fails, Zookeeper will know about that failing node. It also tracks that ISR, that in-sync replica set, and it will handle selecting a new leader to take over in its place. And so in this case, B2 is selected as the new leader. It takes over for B1. Our ISR shrinks down just to B2 and B3. And so we go into this under-replicated state. The second failure mode is the follower failing. And so what this looks like is, so B3 has failed, or it's partitioned from the leader, so it's no longer fetching from the leader's log. And Kafka has this setting replica lag time max milliseconds. This is basically the amount of time that can pass before the leader considers the follower out of date. And so if the follower doesn't fetch from the leader's log in this amount of time, or it doesn't catch up with the leader's log in that amount of time, the leader just says, okay, you're behind, and it removes it from the ISR. We go into our under-replicated state with just B1 and B2, and they're going to continue on as normal. And so B1 and B2 commit message 4 and 5. B3 is still partitioned. And now let's bring B3 back up. It rejoins. It's going to start fetching from the leader, catching up. Commits message 4, commits message 5. Now it's fully caught up. And so at this point, it gets added back into the ISR. We go back into our fully replicated state. So that's how replication works in Kafka at a high level, at least. In NAT streaming, it's a little bit different. So NAT streaming uses Raft to do replication. Raft is a consensus protocol. It handles both the problems of leader election and data replication within this single protocol. And so NAT streaming uses Raft to replicate client state, messages, subscriptions, other metadata as well. And conceptually, there's actually two logs in the system. There's the Raft log, and then there's the message log. So while Raft is a consensus protocol, the way it implements that is as a replicated write-ahead log. And so we have these two logs that we're dealing with. And in a lot of ways, this kind of parallels some of the work going on in RabbitMQ. And last I checked, I don't know if this is released yet or not, but they were working on replacing the chain replication style protocol with a Raft-based protocol. And unfortunately, I don't have the time to go into the details of how Raft itself works. If you're curious, there's a really good visualization if you go to the secretlivesofdata.com/Raft, and they walk through visually how that algorithm actually works and how it handles some of those failure cases that we just talked about. And if you go through that, you'll notice there's a lot of similarities to how the replication in Kafka works. You'll see some similarities between Kafka and Raft. So initially, when we first started this work, we used a Raft group per topic, and then we used a separate metadata Raft group. And there are a couple of issues with this. The first is this problem of scalability. So with thousands of topics, we're going to have thousands of Raft groups. And even with an idle cluster, or with no traffic going through our cluster, there's going to be a lot of network chatter just due to the chattiness of the Raft protocol, because it's doing heartbeats and things like this, as well as the disk activity, because all of those logs are durable. And the second issue is this problem of ordering. So there's increased complexity due to the lack of ordering between Raft groups. Specifically, we have these message Raft groups and the metadata Raft group. And because those are two different consensus groups, we don't have ordering guarantees between those things. So as I said, that there's this issue of scalability. With a single topic, one node is elected leader, and then it heartbeats messages to the followers. And as the number of topics increases, so does the number of Raft groups, because we have this one-to-one mapping from topic to Raft group. And so there's a few things we can do to try to address this. One is we can just run a fixed number of Raft groups and use a consistent hash to map a topic to a group. So rather than having that one-to-one mapping, we have an M-to-N mapping. And that helps with the scalability problem. It doesn't really help with the ordering problem. Another thing we can do, and this is what CockroachDB does, is run an entire node's worth of topics as a single group using a layer on top of Raft. So rather than having all of the Raft groups on a node doing all of their heartbeats to all of the other nodes, we take all of those protocol messages and bundle them up into a single message, essentially, and distribute that to each of the other nodes in the cluster. So CockroachDB uses Raft to replicate key ranges in their database. So you might have thousands of key ranges, and they use this, they call it multi-Raft, which is this layer on top of Raft to try to help with that. And the third thing you can do, and this is kind of just punting on the problem, is use a single Raft group for all of the topics and the metadata. And this solves both problems of scalability and the ordering problem, but it does that at the cost of throughput because we lose the parallelism that we had before. Because with this, all of your topics are being sequenced by one consensus group. So this is kind of the short-term fix. The longer-term solution is probably something more like what CockroachDB does with multi-Raft. And then there's this other issue that I call dual writes. And I mentioned there are these two logs that we're dealing with. There's the Raft log, which does the replication, and then there's the message log, or call it the message store. And that's the log that the user actually interacts with, they deal with. But everything goes through Raft, because that handles the replication. So when a message gets published, it's going to go through Raft. Raft will handle replicating that. And when that message gets committed to Raft, meaning it's been replicated, then we write that message again to our own log, to the message store. But not only do messages go through Raft, also things like subscriptions, cluster metadata, cluster topology changes, and so forth. But every time a message gets committed, we write it again redundantly to this other log. And so we have kind of this write amplification problem. And we can kind of think of the Raft log as this physical offset and the message log as the logical offset. That's what the user is interacting with. And so if we kind of think, if we change the way we think about this and instead treat this other log as the index that we talked about earlier, then we solve both of these problems with this one solution, the problem of the indexing and that write amplification. And so instead of writing the message again on committing to Raft, we just write an index that points back into the Raft log. We get our indexing that way. And so that way I can just do my lookups through the index and I can read sequentially directly from the Raft log. And so effectively we treat the Raft log as our message write-ahead log. Instead of managing these two logs, we just have the write-ahead log and our index that points into that write-ahead log. Okay, so we talked about replication, how we ensure consistency, but how do we keep things fast? The replication is going to come at a cost with respect to performance, and so how do we keep it reasonably fast? And there's a few things we can do. The first is with respect to publisher acknowledgements. We can have the server act on commit, meaning that the data has been replicated. That's going to be the slowest but the safest option. We can act just on writing to our local write-ahead log. So that's going to be faster, but we don't ensure replication. So if that host goes down, we could have data loss. Or we just say we don't care and just fire and forget. That's going to be the fastest but the least safe. The other thing we do is we don't fsync explicitly. And both Kafka and NAT streaming do this by default when clustered. And instead, we just rely on replication for durability. And we make the assertion that if we're running a cluster of, say, 5 servers, especially if we're using rack-aware clustering, it's pretty unlikely that 3 or more of those servers are going to go down simultaneously. And so we just rely on the fact that we're replicating data to ensure its durability. And if we're not okay with that, then we can turn fsync on and sync every write to disk at the cost of performance. And keep disk access sequential, maximize zero copy reads, which we talked about before. And lastly, batch aggressively. And this makes a really big difference with respect to throughput, because if we're doing a round of consensus for every message, that's going to be very slow. And so we just batch up a bunch of messages and then do the consensus on a batch, and that'll be much faster in terms of throughput. And then lastly, how do we ensure data is durable? We kind of touched on that just a second ago, which is we rely on replication. And so quorum is what guarantees durability. Quorum meaning a majority of the nodes in the cluster. And that comes for free with Raft, just due to the nature of that protocol. But in Kafka, we have to do a little bit of configuring. So specifically, we need to set min in-sync replicas and ACKs. So for example, with a replication factor of 3, we would set min in-sync replicas to 2 and ACKs equal to all. And that would give us the effect of a quorum. And with Kafka, we also need to be careful to disable unclean leader elections. So this is basically if all of the brokers in your ISR go down simultaneously, how do we select a new leader? Do we wait for the previous leader to come back up, in which case we might have prolonged downtime? Or do we just select the first broker in the ISR who comes back up as leader? And if, in that case, we might have data loss. But we'll have less downtime potentially. So it's balancing the trade-off between durability of data and availability. So we have this contention basically where durability is at odds with availability. And so if we don't have quorum, then we can't make any progress, we can't allow any reads or writes to happen. Okay, now I want to talk about scaling message delivery. So partitioning is fundamentally how we do this in this kind of system. And it's kind of our unit of parallelism. And it's how we scale linearly in particular. So we have our log and we're writing data to this log, and eventually we're going to exceed the capacity of any one node. And so what we do is just take that and basically break it up into multiple mini logs that we can distribute load across. And that allows us to add more hardware. We can partition our log further, distribute that across those machines, and we get this horizontal scalability. So in this example, we have some kind of e-commerce system. We have a topic purchases, a topic inventory, and we have these each partitioned into 2 partitions. In how we partition our data, that's largely dependent on our application, on our data, the access patterns or the semantics of that data. So, I might partition purchases by account name and inventory by SKU, such that this server or this broker is responsible for this set of accounts, and this other broker is responsible for this other set of accounts, and so on. And there's this other problem of high fan out. And what I mean by that is we have a whole bunch of consumers who all want to read from the same partition. And how do we scale that? And hopefully you can get away with just partitioning to solve this, such that you can partition your data in a way that you can balance your consumers among all of those partitions. But if you have some situation where you have a bunch of consumers who all need to read from the same stream of data, then this can get problematic. And with Kinesis, which is Amazon's version of Kafka, basically, so what they call a partition is a shard in Kinesis, and a shard is limited to 5 reads a second. So if you have a whole bunch of consumers all trying to read from one shard, you either have to coordinate them such that you're not constantly bumping in to that read limit, or you have to do this kind of daisy chaining where you have a shard with some consumers on it, and then you have another shard that's consuming from that, and you chain these up as needed until you meet your capacity needs. And you have kind of this Rube Goldberg-esque solution, which is pretty clunky. And it's worth pointing out too that the replication that we talked about in Kafka and NAT streaming, these are purely a means for high availability. The replication doesn't help with the fan out, with the scalability. But in theory, we could have those replicas serve as read replicas. But with Raft, for example, if we add more nodes to our Raft group, the larger that group gets, the slower that consensus protocol takes. And that's not great either. But with making the observation that with an immutable log, there is no notion really of stale or phantom reads that we might have with like a mutable database where I go to read a value and then I do something and I read that value again and it's changed in the meantime. With immutability, that's not or shouldn't be a problem. And in theory, that should make it easy to scale to a large number of consumers, provided there's some caveats with that, right? One is eventual consistency. So if I have a read replica who's basically tailing the log from the leader, that's not going to be strongly consistent with the leader's log. But if we're just tailing the log, that should be okay because we're going to eventually read all of the records. But if we want to read a particular value, that could cause problems. So with Raft, we can use non-voters to act as read replicas and then balance consumers among those to help with this fan-out problem. And it's also worth, I think, talking about this idea of push versus pull. This is a pretty important design decision in this kind of system. So Kafka uses a pull-based model where consumers pull data from the server. And NAT streaming, on the other hand, uses a push-based model. So the server is actually pushing data out to the consumer. And there are a number of important design implications with this. One is that fan-out that we just looked at. So with a push-based model, if the server is pushing data to the client, that fan-out gets a lot more complicated. Because now we have to coordinate somehow so we know that, okay, this server is going to push data to this set of consumers, and this server is pushing to this other set of consumers. We have to coordinate that somehow, and that gets pretty complicated. With pull, that's not really an issue, right? We just have a bunch of read replicas, and clients are going to pull from a replica, and we can just load balance among those. Flow control is another issue. So with push, we need to push data out at a rate fast enough that the consumer is not just sitting there waiting for work, but we don't want to push data so fast that the consumer can't keep up with it. So we have to have some way to balance that. With pull, this isn't really an issue because the consumer is just pulling data as fast as it can process it. So the flow control there is implicit. Then there's this question of optimizing for latency versus throughput. So with push, I have to answer the question of when I receive a message, do I send it out immediately or do I wait to accumulate a few messages before I send that out as a batch? With pull, it's a question of when I fetch data, I just take whatever is available. But if there's nothing available, do I wait for a few messages to accumulate or do I take the first message to arrive? And then lastly, there's also implications with client complexity. So with Kafka providing a pull-based API, there's not a lot of complexity, or I should say there's a lot more complexity in the client library. The client tends to be thicker with Kafka. There's more work involved implementing a library for that, as opposed to NATS, which is push-based. The client is very thin. There's not that much logic in the client library, and so it's a lot simpler. But as a result, that complexity moves to the server. Okay, we'll wrap up with some trade-offs and some lessons learned. So there are a number of competing goals with this kind of system and really any kind of data system, I think. First, with respect to performance, it's really easy to make something fast if it doesn't have to be fault tolerant or scalable. And simplicity of mechanism makes this much easier. Looking at that storage subsystem that we talked about, using that really simple file mechanism, we were able to take advantage of both the operating system and the underlying hardware. And so it's kind of that mechanical sympathy aspect to this. But at the same time, simplicity of UX makes this much harder. And what I mean by that is, when we look at Kafka, and Kafka, the server really doesn't do that much. There's not that much logic involved in the server. It's more in the client. And with NAT streaming, there's a lot more logic in the server because the client doesn't do all that much. And as a result, with that logic comes performance costs to that. With scalability and fault tolerance, both of these are at odds with simplicity. In particular, when we need to make something fault tolerant, we typically have to replicate, and then we have to deal with replication, we have to deal with consistency. If we need consistency, we have to do consensus. That can be really complicated. And so it really can't be an afterthought. And it's hard to take something that's like a big complex system and just add replication to that after the fact. It really has to be considered from day one. And lastly, with simplicity, simplicity of mechanism tends to just shift complexity around in your system. Looking at Kafka, that's shifting the complexity from the server to Zookeeper to the client. With NAT streaming, it's shifting that complexity from the client to the server. And so it's easy to let the server handle that complexity, and it's convenient for the client, but it's hard when that has to be distributed, consistent, and also remain fast. It's hard to balance all of those characteristics. So aim for simplicity. Distributed systems are complex enough, so simple is usually better, and it tends to be faster too. And I like to reference Systemantics by John Gall, which it's a little tongue-in-cheek, but I think there's a lot of good stuff in it. And one of the things that he says is a complex system that works is invariably found to have evolved from a simple system that works. And I think there's a lot of truth to that idea. And I already hit on this, but you can't effectively and cleanly bolt on fault tolerance. You can't take this big, complex, complicated thing and just tack that on really easily. Instead, and again, referencing Systemantics, a complex system designed from scratch never works and cannot be patched up to make it work. You have to start over, beginning with a working, simple system. And so it's much easier to take something small, simple, and evolve that towards a goal that you have in mind, as opposed to taking this big thing and adding like replication to that. Lean on existing work. Don't roll your own coordination protocol. Use Raft or Zookeeper even. Just don't reinvent that wheel if you don't need to. And there are probably edge cases for which you haven't written tests. There's so many failure modes and only so many tests that you can write. And so things like formal methods and property-based testing, generative testing, these can help a lot here. Jepsen is a really good example of this, I think, as a way to verify the correctness of your system without having to write thousands of large end-to-end integration tests. And lastly, be honest with your users. Don't try to be everything to everyone, but be explicit about design decisions, trade-offs that your system makes, guarantees that it provides, default settings, and so forth. I think a lot of vendors tend to be kind of disingenuous with some of these things, especially when they kind of talk about what use cases a system is well suited to and what, which ones it's not particularly well suited to. So I think it's better just to be honest and upfront about these kind of things. So if you liked this kind of stuff, I did a series of blog posts on this topic that go into a lot more depth. And then I ended the series by laying out the design for a new system that kind of builds on a lot of this stuff. So you can go and read that if you're interested. And that's it. Thank you.
Awesome. Thank you, Tyler.